Okay, so let's do this question. Okay, so we don't have any rules yet, right? So we can't use any, in 2.1, right? We don't have any derivative laws. The only thing we have is that the limit, so what would f prime of 0 be? It would be the f prime of 0 is equal to the limit as x approaches 0. True, it is continuous. That's good. This is continuous. So that's good. I mean, if it's not continuous, then it certainly would not be, the derivative would not exist, right? Continuous by squeeze theorem, right? So that's a good first place to start. Okay, limit as x approaches 0 of f of x minus f of a over oh well, it's not. I can't. I can't use this. Oh no, sorry. Yeah, my bad. Wasn't thinking. F of x minus f of a, or a is 0 in this case, over x minus 0. Okay, so what is f of x? As x approaches 0, what is f of x? And it's very important what this means. As x approaches 0, what is f of x? Not when x is 0, but when it approaches 0. Which function do I look at when x is approaching 0? The first or the second? Not when it is 0, but when it's approaching 0. The first, yes. That's what we write for in our f of x. Now, what's f of 0, though? Yeah, f of 0 is 0. So this is interesting. What's the answer, you think? Does it exist? If it exists, that means this limit exists. Does this limit exist? No. Does not exist. So no, it does not exist. Yeah, makes sense. So today we'll actually find out how to take the derivative of this function. And in fact, we'll see that if this was x cubed, sine of 9 over x squared instead, or 9 over x, this limit, the derivative would exist here at 0, surprisingly. We'll do that like at the end. So we'll find out, we'll be able to determine how to find the derivative of this. And mainly the one that we don't know yet how to find the derivative is the derivative of this. It turns out that the derivative does exist at 0 if you allow this to be 0 at 0. Okay, good. So any questions about that? So again, this is just using definition of the derivative. Okay, so let's continue. So last time we developed the quotient rule. So I thought we could do the derivative of this famous trig equation. So we saw that what is the limit as x approaches 0 for this? Sine of x over x? Do you remember that? Should remember that. That's an immediate. Yeah, it's 1. And if you think about it, you do this by squeeze theorem. What's the limit as x approaches infinity of sine of x over x? Think about squeeze theorem when you answer. 0, yeah. Right, sine is between 1 and -1. Then if you multiply by x, then everything goes to 0. So what this kind of looks like, there's a lot of oscillation happening over here. And then something happens at 0. And then it squiggles off to infinity. So how can we figure out what's happening at 0? So this limit could help us understand what's happening at 0. Like if we zoom in here into this red section, we don't know what's happening. Maybe it oscillates more. Maybe it comes down and then up into the point. So we don't really know. But what would this limit tell us? It tells us if does it flatten out here? Does it come up to the point like with a positive derivative, or does it come down to the point with a negative derivative? So this limit can help us show that. Okay, so first of all, we need to take the derivative. What's the derivative of that? What rule do we need to use? Quotient, yeah. Okay, so what is the quotient rule again? It's the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator divided by sine squared. Okay, what's the derivative of sine? Right, cosine. So you have x cosine x. What's the derivative of x? 1. So we have minus sine of x. Okay, thoughts on how to continue this limit? Those are on the next page. How do we continue this limit, you think? Any thoughts? Just coming back from our quiz on limits. Is there an identity that you see? Take x out. Okay, yeah, okay, I see. Good. Yeah, so if you take an x out from the denominator and numerator, you get cosine minus sine of x over x, then x. Good. So this cancels. And what is this limit? Right, this goes to 1. So what we're left with is cosine of x minus 1 over x. How do you find this limit? Remember that one? This this looks close to something, right? What can I multiply cosine x minus 1 to make a Pythagorean identity? Or, yeah, to make a Pythagorean identity. Very similar to our how to deal with radicals trick. Anyone? Yeah, so the radical trick was conjugate, so we don't call it conjugate here, but the idea is similar, is that we realize that this is a factor of the difference of two squares. And what is the difference of two squares? Here, it's nice, it's cosine squared minus 1, and we all know what that is. What is cosine squared minus 1? Almost sine squared. It's not sine squared. Well, this one is sine squared, right? So remember, it's cosine squared plus sine squared is equal to 1. So what if you have cosine squared minus 1? It's actually negative sine squared. Yeah. Not that it matters here, because it's going to end up being 0. Because we have a sine of x over x. And then we have negative sine of x over cosine plus 1. And this is going to 0. Okay, so what does this tell us is that in our graph for sine of x over x, so we had this stuff going on. So it actually does flatten out at the top here. So it doesn't hit here, but it flattens out. Okay. Any questions about that? Okay, so let's do some more. Okay, I have one here. Let's say you have a polynomial, and the degree is m that's less than n, a number. Can someone remind me what is the degree of a polynomial? What do I mean when I say the degree of the polynomial is m? What's a second degree polynomial? What if polynomial has degree 2, what does that mean? Yeah, just exactly the highest degree of x with non-zero coefficient. Okay, so now thinking about that, if m is the highest degree and m is less than n, what do you think the nth derivative is? And just do a little quick example. And you'll see why this is true. So for example, this is a second degree polynomial. So it's like my m. And this is 3 derivatives. This is my n. So what is this third derivative? It's 0, yeah. So to see that, what's the first derivative? What's the first derivative of x squared plus x plus 1? Yep, it's 2x plus 1. So take another derivative. What's the derivative of 2x plus 1? Yep, it's 2. And then what's the derivative of 2? 0. So what happened at every stage? What happens to the degree of the polynomial at every stage? Right, so if p is degree so if p of x is a polynomial of degree n, what is the degree of the derivative? Right, n minus 1. Right, if all you're doing is subtracting 1 to the powers, polynomials are all powers of x. It's certainly not going to add to a degree, right? And if you have ax to the n, and we multiply, and if this turns into ax to the n minus 1, well, this is never going to be 0, right? So you can't get that term can't disappear, right? So it's guaranteed to always be of degree n minus 1 when you take the derivative. So now if you take more derivatives than there are degree, then eventually you'll 0 out, right? For example, if you take 3 derivatives of a second degree, you get 0. But notice that if you take 2, that's why it's strictly less than and not less than or equal to. If you only took 2 derivatives, you were left with 2. So there's something cool about polynomials, that the derivative has a very nice, it's very formulaic with derivatives. You just subtract 1 to the degree of the polynomial. Okay, any questions on that? Okay. Okay, let's do the derivative of sine of 2x. Okay, how do we do this without, with only using the rules that we know? Good, yeah, knowing the double angle formula. Uh, 2 sine of x cosine of x. And now what? Yeah, product rule. And I would want to say, let's take out the 2 first, because it would add unnecessary complication. So it's just derivative of sine times cosine, and then use the product rule. So 2 So derivative of sine is cosine times cosine plus the derivative of cosine is negative sine times sine. So we get 2 cosine squared minus sine squared. What is cosine squared minus sine squared? Really start memorizing these formulas if you haven't. They're just good to know. Yeah, cosine 2x. It's the double angle formula for cosine. Okay, so there was some work here. It took some work. So today we're going to come up with a new formula that will do this in like one step. And so let me ask you, what type of function is sine of 2x? It's not a product, right? It's not a sum. But it's a combination of functions, right? What do we call combinations of functions? What's the word for when you do one function and then you do another function? You do 2x first, and then you do sine. Composition, remember that word? Okay, so if the goal is that if we know how to take the derivative of a composition, then we don't have to deal with angle formulas, right? For dealing with like sine of like 2x, for example. If we can just deal with how to take the derivative of sine composed with 2x, then maybe it'd be a lot easier. So for example, this will help us with like sine of 1 over x, for example. There is no, at least not that I know of, nice reciprocal formula for sine and cosine. But when finding derivatives, it turns out we don't need such a formula for angles like reciprocals. So we can just come up with a formula that will just deal with composition functions entirely. So this is going to be called the chain rule. So why is it called chain rule? Is that in a composition there's there's a chain of functions. Like each function is like a link in the chain. So this is the formula for derivatives of compositions. Okay, as with everything, we have to prove this before we say it. So, but we're going to give ourselves some stipulations. So let's think about the composition f of g of x. And here are the things that we want to be true. Let f prime of g of a and g prime of a exist. Turns out these will be necessary. Can someone tell me what f prime of g of a is? Like, how do you read this? Just in terms of composition, how do you read that? So it's f prime of x and then plug in A into G. Then you plug in G of A into F prime of X. So just don't, if you don't remember that, how that reads, that's how you read it. So it's G of A plugged into the derivative. And then it turns out we'll also have to think about the derivative of G as well. Okay, so let's do it. So as with anything, f of G of A, or f of G of X at A, is the limit as x approaches A of what? F of G of X minus f of G of A over x minus A. So now, so let's say if you were developing this for yourself for the first time, you might think that G prime should be required. So what can I do to this to force a G prime to appear? Where is the derivative of G? Like, what should I multiply this by to give me a G prime? So like, what should go here in the numerator? Yeah, if I have G of X minus G of A, then suddenly this term becomes G prime. So that's the main step to this question, or to this proof. So G of X minus G of A over X minus A. So cool, we have the derivative of G that pops up. So now, all we have to do is really work on this side. So I'm going to do a little trick. It's called changing variables. Because this term here looks eerily like a derivative, right? I'm going to let u equal G of X. So if I do that, then we get f of u minus f of G of A over u minus G of A. Okay, so this looks, if I took the limit of this as u goes to 0, what is this as u goes to 0? You could even, if you want to change some more things, let b equal G of A. What is the limit as u approaches 0? So u is like your new x. So pretend u is just x all along. And what is f of u minus f of b over u minus b? as u goes to 0. But u doesn't matter, right? Yeah, it's just a derivative. It'd be f prime of b. Right? The u doesn't matter because I'm taking u to 0. It's the variable I'm taking to 0, so that's why it's the derivative. X isn't special, right? It's just a variable. So this is f prime of g of a. So we're going to manipulate a rule of limits about continuous functions. Derivative separate. Yeah, so yeah, the chain rule is like inception for derivatives. Yes, derivatives within derivatives. So I'm going to say h of u is a function that's going to be continuous. We'll see why. Is that it's this expression when u is not equal to g of a, and it's equal to f prime of g of a when u is equal to g of a. Someone say why this is continuous? I'm sorry. I put u to 0. That doesn't make sense. U is going to b. Sorry, that was confusing. Why is this continuous? What's the only problem? Or let's say, rather, it's continuous at g of a, to be more specific. Maybe we don't know what's happening at other points. But at g of a, we know it's continuous. Yeah, the top limit exists because that's just the derivative, as we established here. And the bottom limit is that limit. Good. Okay, so let's plug in u back into g of x. So we have the limit as x approaches a of h of g of x, and then we have our g of x minus g of a term. So since this is continuous, what is a limit as x approaches a of h of g of x? What can you do to continuous functions for limits? If you know it's continuous, what can you do? You can just plug in the point, right? When a function is continuous, you can just plug it in. So what is it at a? It's this at a. And hence g of a, right? U is, as x approaches a, g of x is going to g of a, which is u. And then what is g of x minus g of a? Well, we had established that this was g prime. So that's the derivative. Okay, so questions on that? So the derivative of f of g of x Let's use ddx. So I don't like writing all those parentheses and primes. ddx of f of g of x is f prime of g of x and g prime of x. This is called the chain rule. Okay, so let's use the chain rule to take the derivative of sine of 2x. Okay, so first we have to say what is f and what is g. What's f of x in this case and what's g of x? Yeah, sine is sine is f. Yeah, so if you want to think about it, f is the function you plug into, and g is the function you plug in. Yeah, so f of x, what are you plugging into f of x? You're plugging in sine, or you're plugging it into sine. What do you plug in? You plug in 2x. Sometimes you might call f the outer function and sine the inner function, because it's inside. But sometimes this terminology can be misleading based on like how symbols are written. Okay, so what is the derivative then? F of g of x prime is, so I need to find f prime and g prime. What's f prime of x? It's cosine. And what's g prime of x? 2. Okay, so what's f prime of g of x? So I'm plugging in g of x into the x for f prime. Yeah, so f prime of g of x is cosine of 2x. So I'm plugging in 2x into x. And then multiplied by g prime is 2. 2 cosine 2x. So it's kind of a quicker way of doing this than using the double angle formula. Right, in this case, we didn't have to use a double angle formula for cosine, right? It just popped up naturally. So questions about that? Okay. So we can do another one. That we used the product rule before, but now we don't need to. Oh yeah, by the way, I think at 6:30 we can take like a 5 to 10 minute break. So just remind me around 6:30, and then we can just take a short break. It might be good just to kind of like rest our eyes from math for a little bit. I did that last class, and I think it helped. Okay, so we used the product rule before to deal with sine squared of x, but here we can actually use the chain rule. So this is why outer inner is a little bit misleading. If you've heard of that, outer inner. First of all, what are the two functions? What is the function that you plug in, and what are you plugging into? It's harder to see for something like this. Any ideas? How about if I wrote it like this? What do you think the two functions would be now? Or at least one of them. Yeah, which is sine? Is it f or g? F and g. Okay, we'll do this also. Yeah, it's x squared is f. If sine was f and g, this is what it would look like. We'll do that one as well. You're plugging sine of x into sine. But yeah, in this case, f is actually x squared, and g is sine. Right? You're plugging sine into x, and then you're squaring it. So the squaring function is a function. Okay, so we need f prime. What's f prime? Two x, and then what is g prime? Cosine, yeah. Okay, so what is f prime of g of x g prime? So what happens when you plug in g of x into f prime? To sine. You're plugging in g of x, not g prime. So you're plugging in g of x into f prime. So it's 2 sine of x. And then you multiply by cosine. That's g prime. And then that's the double angle formula, sine 2x. Okay, questions about that? Okay, so let's actually do this example. Okay, so we established before that f was equal to sine and g was equal to sine. So we know what the derivatives are. So the problem is how do you arrange it? So f prime g of x, g prime of x. So f prime is cosine. And what do you plug into cosine? You plug in sine. And then you multiply by cosine. Okay. Questions about that one? Okay. Let's do secant. So last time we did the derivative of secant using the quotient rule. But in fact, can someone tell me actually? How can I view this as a composition? Good, yeah. Yes, that's one of the compositions. Good. So it's like cosine to the -1, or in either way you can view it either way. So yeah, so we have f and g. So one of them is 1 over x and one of them is cosine. So which is which? What is the function you're plugging in and what are you plugging it into? Yes, you're plugging it into 1 over x, and what are you plugging in? You're plugging in cosine. What's f prime? What's the derivative of 1 over x, the derivative of x to the -1? Good, -1 over x squared. Right, because it's -1 times x to the -2. And then what's g prime? What's the derivative of cosine? Yes, negative sign. So we put it all together. So f prime is -1 over x squared, so it's -1. And instead of x, I put in g of x, cosine squared, multiplied by negative sign. So this is sine over cosine squared, and we know is secant tangent. Okay, questions about that? Okay, let's do more. Let's do the derivative of secant of tangent. Let's be a little bit more spicy and say tangent x squared. Okay, what's f and g? Yeah, which is which? Secant is f or g? Yeah, f is secant. And what are you plugging into secant? Tangent x squared, yeah. Okay, what's the derivative of secant? We had just done this, so that's secant tangent. Now, what is the derivative of tangent of x squared? Yeah, so now to find the derivative of tangent of x squared, I need to do more. So let's let u of x, let's let that be the f, and v of x be the g. So for tangent of x squared. So which is u and which is v? Yeah, so you see like one of my things in my chain was a composition itself. Yeah, so my first function is tangent. My second function is x squared. So I have u prime of v of x and v prime of x. So what is u prime of x? It's derivative of tangent. Yep, that's secant squared. And then what is derivative of x squared? It's 2x. Okay, so what is g prime of x? So it's u prime, which is secant squared. And in place of x, you plug in v of x, so x squared. And then you multiply by v prime, 2x. Okay, everyone follow so far? So we needed another chain rule in order to do the derivative of one of the functions. Okay, so now let's apply the chain rule. So f prime is secant tangent. So in place of x, plug in g. So x appears twice, so you have to plug it in twice. So all of this is just f prime of g of x. And then you plug this in. 2x secant squared of x squared. That's it. So I think a challenge with the chain rule is to stay very neat and organized and not be messy. So yeah, just be careful with that. Okay, everyone okay with the double chain? All right, so we'll take a little break, but I'll leave you with a question or two while we take our break. Is it glitchy? Okay, so let's meet back up at 6:40. But between now and then, you can ask me questions. And yeah, look at these if you want to keep going. So yeah, any questions? Want to go back to a previous page for clarification? Just let me know. No, you don't always have to. I mean, the homework might ask you to, though. It's good practice for how to write compositions. But I mean, if you have seen this before, then maybe not as necessary to write it every single time. But I do guarantee it would be helpful for very complicated chains. Um, so it's good practice, like to do it for some of the simpler ones. But like if there gets to be like a lot of chains, it's helpful to write everything out. But no, I mean you don't really have to. Yeah, I think like if you kind of like write all that out, like this one, I don't think I could just do right away in my head, right? I think that'd be take a lot to come to this. I definitely have to write this out. I mean, I do agree. The f prime of g of x is not the hard part, but yeah, it's hard to keep everything in your head, I would say. By the way, I think after we have the chain rule, we're at the point where you can make your own practice problems. You can do any combination of products, quotients, and compositions, and you can find their derivative. Right? There's not many things we don't know the derivative of right now. Right? We don't. The only things we don't know are like exponentials, logs, and like the inverse trig functions. Right? And all those you do in Calc 2. So we pretty much covered every single like after chain rule. We're done with like all the derivatives that we know how to do. So then like from here on out, it's like all application, like after chain rule. But so it's very easy to come up with your own practice problems. Just every combination you can think of. All right, 6:40. So why don't we come back? Hope that was a nice little break. I think we'll do it from now on. Okay, so let's do this first one. Can someone tell me the F and the G? Good. X to the fifth. And then what's the G? Yes, x squared plus 1. So then you have f prime of g of x, g prime. So it's plug in x squared into the, we should find the derivative first. What's the derivative of x to the fifth? Yep, 5x to the fourth. And then the derivative of g prime. Or derivative of g. Yes, 2x. Okay, so plug everything in. So plug in g of x into 5x to the fourth. You get 5 x squared plus 1 to the fourth, and times 2x. So you get 10x x squared plus 1 to the fourth. Why this is a nice example is that this says if you have a product of polynomials, you do not need to expand everything out and then take the product. If you just treat this as a chain rule, then you don't even need to think of it as a product, but you can think of it as just a chain rule. Okay, what's the next hardest one? Probably the tangent one. Okay, what's F and what's G? Yep, x to the fifth is the F, and then G is the other one. Okay, what's F prime? Yeah, same one as we had before, 5x to the fourth, and then G prime is secant squared. Okay, so let's do it. F prime of g of x times g prime of x. So it's 5 tangent to the fourth of x times secant squared of x. Can't simplify that because right, tangent is sine over cosine and secant is 1 over cosine, so this is fine. Questions about that one? All right, so let's do this one. Cosine of cosine of cosine of x. Okay, what's F and what's G? So by the way, usually what I do for when you have a lot of parentheses is to kind of alternate between parentheses and brackets. So I think it helps. Yeah, so the big one is f of x, or is cosine, and then cosine of cosine. Okay, what's f prime? Yep, negative sign. And then g prime. So we need to do another chain rule, right? So I like to use u and v. So what's the u and what's the v? There's not much choice, right? It's cosine and cosine. So u prime is negative sign. And v prime is negative sign. Okay, so this is where things get interesting. Okay, so what is u prime of v of x? It's negative sine of cosine of x. And then v prime is negative sine of x. So putting it together, we get sine of cosine of x, sine of x, because the negatives cancel. Okay. Move this down. Okay, so let's do the chain. So all of this is g prime of x. So what is f prime of g of x g prime? So you should be very careful about plugging things in. So f prime is negative sine. What do you plug in? You plug in cosine, cosine. And then you multiply it by sine of cosine times sine. Say that 10 times fast. Okay. So questions about this one? So you should be very careful, but it's okay. Questions? Does everyone follow? All right, great. Okay, so let's do this one. A new page. So the limit, so x goes to 0 of the derivative of x cubed sine of 1 over x. And again, please stop me if something's not clear. Okay, so how do we take this derivative? So now we've developed the chain rule, we don't need to do what we did in the beginning, right? Well, this one was a little special, but we can actually use the chain rule now to to find this derivative. So how do you find this derivative? What do you do? Yeah, so first and foremost, this is a product. So we need to use the product rule. So product says, take the, let's first have this limit in here. You take the derivative of the first times the second plus the first, and then times the derivative of the second. Okay, so let's deal with this first. Derivative of x cubed is 3x squared. Okay, so now we need to find the derivative of sine of 1 over x. So how do we find that? How do you find the derivative of sine of 1 over x? Yes, this is a chain rule. So what is the f and what is the g? So what is the function you're plugging in, and which is the function you're plugging into? Yep, f is sine, that's the thing you're plugging into. And g is 1 over x. Okay, so what's f prime? It's cosine, and then what's g prime? So if you always forget that, just remember it's x to the negative 1, and then use the power rule. Good, yeah, so it's negative 1 over x squared. And via the power rule, you can see it as negative x to the negative 2. Okay, so let's plug everything in. F prime of g of x, g prime. Okay, so f prime is cosine. And you're plugging in g of x, 1 over x. And then you multiply by g prime, negative 1 over x squared. Okay, so now we have an expression for derivative of sine of 1 over x. Does anyone know what the limit is? So just to see, I might as well write it in. So there was an x cubed here. So there's an x squared now in the denominator. Anyone know what the limit is? as x approaching 0. Good, yeah, it's 0 because by the squeeze theorem. For each of these respectively are squeezable functions, right? Sign is between 1, -1, and then when you multiply in the x squared, it squeezes to 0. Similarly, this squeezes to 0. So notice, so I'll let you try to do it. Well, actually, for the one on the homework, it was just an x here, right? And we saw that the f prime of 0 did not exist. Well, first of all, just because the derivative just doesn't make sense. But somehow, when you have x cubed, it does work. So so let's see, I have a picture. Let me try to share my screen. So on the recording, this might not show, but hold on. Okay, everyone see that? Again, this might not show on the recording. You see the Wolfram alpha? Okay, yeah. So here we have sine of 1, x sine of 1 over x. So by the squeeze theorem, it's squeezing down to 0. So if you zoom in, that's the picture that's going on. This is squeezing to 0. However, the derivative does not squeeze to 0. Actually, probably should have done the derivative. Can I do that? Yeah, so this is the derivative, which who knows is going on at 0. That's a lot of oscillation going on. But now let's look at x cubed of sine of 1 over x. So this is what x cubed looks like. And notice that, in a way, it's like approaching 0 faster. It's one way to kind of understand that. Like, it's going to 0 very quickly, right? Whereas for x of sine of 1 over x, it's kind of a more gradual descent. So if you want to think about in the squeeze theorem, x of sine of 1 over x, what is squeezed by? It's squeezed by x cubed and negative x cubed. So the cubic function approaches 0 faster. So that's why this looks different. So now let's take the derivative, which we found, and we saw that the limit was 0. Now the derivative, look at the derivative now, it's approaching 0. There is a clear distinction about where the derivative is approaching. So do you see that, the difference between the two? So this was the derivative for x sine of 1 over x, which just looks very weird, precisely because the limit at 0 doesn't exist. But this was the limit of the derivative at 0. There's actually something that's approaching. Do you see the idea there? And if you look at the picture for the x cubed sine of 1 over x, it makes more sense, right? Look at this graph. It makes sense that the derivative is approaching 0, right? If you were to sketch the derivative, this looks like flat near here, right? Does everyone see that? there's a lot of oscillation going on, but it's like the oscillation is like decreasing as I'm getting closer to 0. However, for x sine of 1 over x, like it's not, the curve isn't flattening out, right? The curve is squeezing towards like a straight line rather than a flat line. So questions about that? So just to kind of just see the intuition. And you can always graph all these, you know, it's a program I like to use, Wolfram Alpha. You can graph them to kind of visualize like really what's going on in the derivative. So again, if you look at the squeeze theorem setup, sine of 1 over x is bounded by this cubic function. And it's approaching 0 a lot faster than our x sine of 1 over x. You can also see that in the derivative too. What's the derivative of x? It's a constant, it's 1. Right? So it's like the flat rate at which it's decreasing to 0. But the x cubed, it's decreasing to 0 a lot quicker. Right? The bounds are decreasing to 0 a lot quicker. So, I don't know. So I think it's nice to see that. Yeah, so like if you ever see like an interesting looking equation, you know, for a derivative, I think it's always fun to just like graph it on some computer program and like observe it, and then you can, you know, see how your derivative makes sense. Okay, anyway, any questions about all this? Okay, so let's just do more problems. Let's do derivative of sine of x squared minus 1 over x plus 1. Okay. What's my f and g? Yep, f is sine, and then g is the other one. Okay, and then what's f prime? Yep, cosine. And then what's g prime? How do I find g prime? Quotient rule, yeah. So, derivative of the numerator is 2x times the denominator, and minus the derivative of the denominator is 1 times the numerator over the denominator squared. Okay. That's a kind of complicated g prime, right? Can I simplify that? how do you simplify this? Okay, yeah, so so you cancel out the x plus 1. And there are different functions, right? So the but here we can, if we make this x plus 1, x minus 1, so let's do this one first. Then this becomes x minus 1 and then x plus 1. Yeah, so this is x plus 1 over x plus 1 is 1. What happened? Should that happen? Yeah, so yes, yeah. So if you notice over here, if you factored this, this is equal to x minus 1 when, is it equal to x minus 1, by the way, or what is it equal to? You have to be careful, right? You have to say x cannot equal 1. So notice that the derivative is not quite the same because you have to say x not equal 1. Because at this step here, or even this step here, you have to make the claim that x cannot equal 1. So g prime is not 1, but it's 1 with the restriction that x can't equal 1. Or negative 1, sorry, not 1. Everyone see that? Just, if you were to state the derivative, you can't allow for negative 1. Okay, so let's do the derivative. So it would be cosine. And surely we can put x minus 1 as long as we say that it can't equal negative 1. Yeah, so here's the big problem. This is not the derivative. Right? This is the derivative. So you see the difference there? So if you're quick to cancel out the factors, you might just say it's cosine of x minus 1. We might forget that x can't equal negative 1. So if you were to graph this, we know actually what this looks like. Anyone know how to graph cosine of x minus 1? Remember how to graph that? Yeah, good. It's a shift to the right. So it would be, so that's cosine. So I'll do it like that. So wherever negative 1 is, don't really know where, what quadrant that is, because this is radians. Let's pretend it's here. Let's say that's negative 1. That would be an open circle. Yeah. Okay. Yeah, so just a good example of the derivative has to exist in its domain. Sorry, it's the opposite of that. Derivative cannot exist if the function does not exist. Okay, so actually speaking of graphing, next time we're going to be talking about using the derivative to graph. Is that what we're doing next time? Let me check. Oh no, we're not doing that next time. Okay, so here's a motivation for next time. Let's find this derivative. Okay, so what's f and what's g? Yep, f is radical x, and then what's g? Is the other thing, yeah, 1 minus x squared. What is f prime of x? So it's a power, right? So x to negative 1/2, but also times 1/2. Yeah, so you can also write this as 1 over 2 radical x, because the negative will be in the denominator. And then what's g prime? Negative 2x. So what's the derivative? So we have 1 over 2 radical 1 minus x squared times negative 2x. So this is negative x over radical 1 minus x squared. What's the domain? First of all, what's the domain of f, or of the function, not the derivative? It's the domain of the function. Good, yeah, the domain of the function, that's this one up here, is including 1 and negative 1, negative 1 to 1. Why is that? Because negative 1 minus x squared has to be greater than or equal to 0, which means that if you split it up, 1 minus x and 1 plus x, then you can do it, that check, that it's positive for things in between negative 1 and 1, and it's negative on either side. So knowing that, what's the domain of the derivative? So we'll do more of this next time, but this is, if you remember polynomial inequalities, that's what you would look for. Yeah. Yes, this is open circle, open bracket negative 1 to 1. Because you don't want it to be 0 in the denominator. Now finally, what is this function? This is a well-known function. Do you have an idea? What's the range of the function? So you can only plug in, good, it's a semicircle. So range, yeah, so speaking of that, what's the range? So you know it's a circle, and we'll explain why, but let's first do the range. So when you plug in values between negative 1 and 1, what's the smallest thing that can pop up, and what's the biggest thing that can pop up? Zero and 1, yeah. When you plug in 1, you get 0, you can't get something negative, because it's the square root, and the maximum thing you can get out is 1. Yeah, so why is it a semicircle? Well, if square root of x squared minus 1 minus x squared is y, let's square both sides, and you get 1 minus x squared is equal to y squared. And you have 1 is equal to x squared plus y squared, which is a circle. Why is it a semicircle? Why was the correct answer a semicircle, not a whole circle? Yeah, it has to be positive because of the square root, right? There's no plus or minus for a function. So what we're going to do tomorrow, or not tomorrow, but next time, is can we just take, and this is going to be in quotes, can we just take the derivative of the whole circle? So we can take the derivative of the half circle. We can take the derivative of the other half circle. So what's stopping us from just taking the derivative of the circle? Well, first of all, what is stopping us? What is just a natural barrier to stopping us from the derivative of a circle? What do you think? Does it even make sense to find the derivative of a circle? And the derivative is this limit. Yeah, something's off here. Yeah, it's precisely because it's not a function. Yeah, so when you take limits, right, you have to say which you're going towards. Are you going towards as x is approaching here? Which tangent line are you looking at? Are you looking at this one? Or are you looking at this one? If you're not infinite, just 2, right? There's, for every point, maybe except these outer ones, there's 2 tangent lines at a point, right? It's either the one on the upper circle or one on the lower circle. However, I mean, it should make sense that the derivative does make sense everywhere, right? Because it makes sense on the upper circle and it makes sense in the lower circle. So, yeah, next time we'll talk about how to make sense of it on the whole thing. And this can be extended to other types of objects that are not functions, like an infinity symbol. It's called a lemniscate. The derivative can make sense everywhere if you ignore everything else, right? But you still have this problem where the derivative may not be a function, but the idea is, and this is a weird word, locally, the derivative is a function. So how are we going to treat derivatives? This is kind of how we always treat derivatives, is that when you take a derivative, you don't care about anything else except at the point you care about. So before next time, we've always treated derivatives like you don't care about anything else other than this little section here. All you care about was happening really close to the point, right? But we're going to like kind of narrow our view of the derivative and say, no, we're only going to look at the derivative around the point, around the y value, rather than around the x value. We're going to care about what's happening around the y value. By doing that, then we can make sense of the derivative that, well, there's only one derivative in this circle here, right? We don't care about this one in the bottom. So this we'll do next time. This is called implicit differentiation. So it's a way to differentiation. It's a way to understand the derivative. Really, what it's doing, the derivative is at a point. You really shouldn't think of the derivative as a function, because oftentimes, particularly like the circle or this infinity sign, you cannot see the derivative as a function. But however, it does make sense as an object worthy of study, right? You probably should want to think about how is the circle changing. And just because it's not a function, why should we just kind of ignore that? So we'll explore more of that next time. And there's a lot of cool shapes we'll find the derivatives of, in quotes. But yeah, we'll do that next time. All right. Have a good weekend. I'll see you Tuesday, unless there's a holiday that I don't know of. But you should get the quiz grades, by the end of the weekend. But you should already know kind of what your quiz is. Okay, I'm going to stop recording.